Welcome to week 5 of Advanced Object-Oriented Programming. This week we're going to be jumping into looking at design patterns, solid principles, and architectural intent. So looking at kind of where we've been so far, we've talked about generic type safe abstractions, collections and performance reasoning, exception handling, and defensive design. Today we're going to look at patterns. That'll be the major concentration, where we're looking at types of creational patterns when we're creating objects, structural patterns, how we build objects or what are the internals of it, and behavioral patterns. If we want things to behave in a particular manner, what kind of patterns do we have that we can kind of piggyback on to get our system to act a certain way? And then we're going to look at composition and inheritance, and then look at solid principles, which is an acronym that gives you the overall 5 basic items you want to make sure that are in your design of objects. And recognizing when recognizing when we're misusing patterns. Patterns aren't for everything. Okay, so we're going to be talking about, well, what are the warning signs when we know that we're maybe going a little over the deep end in using patterns. And then communicating architecture intent. Why did I use a given method or a given pattern in order to accomplish what I'm trying to accomplish? Okay, so part 1, we're going to be talking about creational patterns. And creational patterns are going to fall into the category, go back up here, either singleton, factory, abstract, or builder. Okay, so those are the creational patterns that we're going to be reviewing. Now, again, as in always, I'll put a little statement out here. I am not really that concerned with you knowing the exact syntax, using the exact example that is given. What I am looking for you to do is know when you're in a situation where you need a singleton. Okay. You want to create a design for a singleton. Well, what does that mean? That means that there are certain conditions where, if I meet this criteria, what we're getting ready to talk about, I would say, that is a singleton situation, and I need to do some additional research into what makes a singleton pattern. Okay. So once you do that research, you'll be basically delving into what we're getting ready to talk about. Now, you'll have to do some deeper digging because, again, when I talk about, we have a trade-off of global state. What does that mean? Okay. I don't think it's useful for me to, we do have a definition of terms that we're going to be utilizing, but I don't think that, having a specific definition here at this time is going to help. What I want you to know is if I have a situation where I need to create an object, but it meets criteria A, B, C, D, E, then I know, that's a singleton pattern situation. So let me look at singleton and see what requirements I need in order to do that. Okay, that's the way we're going to be approaching things. So here, singleton ensures only one instant exists. This is a situation, in this particular example, is looking at a configuration manager. I only need one of them. Only one of them should be active. So this basically pattern ensures that only one instance of this particular class exists, or this object exists. So we use, when shared configuration, centralized resource manager. That is our need. Trade-offs is, global state is harder to test, can violate dependency inversion. What is a global state? Data that is shared, accessible throughout the program, often by many classes or components. Okay, so this particular object is global in nature. Harder to test. Okay, that's a trade-off. When code depends on shared or fixed components, it becomes difficult to isolate and test individual parts of the system, because if you uh, take one instance of doing that test and the trade-off, you're not in a situation where we're going to be talking about later about concurrency to get the exact situation in the environment that will actually be what you're running in production. Okay. So it's harder to test when I only have one item that is basically driving the whole process as far as a single tool. Okay, dependency inversion principle, just kind of highlight this. The principle stating that high-level modules do not depend on low-level modules. Both should depend on abstractions. And what we want to do as much as possible is use interfaces. Interfaces and abstract classes. That gives us the most flexibility that we can use and need is by using interfaces and classes. And that's called dependency inversion principle. Here is just a simple idea of how we're using that. Instead of saying order, depends directly on my database, I'm basically going to put in a placeholder called my database. And then now, once I do that, I can implement different databases. Okay, I can implement SQL, I can implement DB2, okay. I can implement Progress, SQL, okay. So how I structure this, okay, how I structure this is I'm removing that dependency of, in essence, of hard coding, okay, and that's what we're talking about here. The factory pattern encapsulates object creation, allowing methods or class to decide on which object to create. Here, this is just a clean view of here. I'm creating a class, and this is the example we're using the shape factory. Okay, I can do circles, I can do squares, I can do triangles. Okay, so rather than creating a class for each individual one that I'm going to create, what I can do here is place all of those in a shape creation class. And then from there, I can add to it and subtract from it, have security in there that says, okay, if it's not one of these squares or not one of these shapes that I want to allow use of, okay, then I can basically say that, nah, can't do that. But the key thing here is I can add other shapes. I can add circle, I can add square, I can access triangle. I can access rectangle. Okay, so I can add, okay, to that. And that's what we're going to be defining here is the open close principle, is that open close is a design that allows new functionality to be added without modifying existing code. So I can update this class, okay, and add to it, but I'm not affecting what's already there. Okay, that's a factory pattern. I'm creating multiple classes. I'm creating multiple objects from multiple classes. And we're using that. Factory means multiple creations. Okay, so we got the open close principle, as far as being able to add without modification. Okay, we also have what we call an abstract factory, and it creates families of related objects. In a nutshell, what this is basically doing is having, if I have a situation where I have different classes or different objects that need to act the same, okay, even though they're not the same object. That's where we use an abstract factory. The abstract factory pattern creates groups of related objects through a common interface without the client knowing exactly classes being created. Okay. Because you're only concerned with one of the particular classes that need to be created, and you're really not basically looking at what other objects are created. So for example, here, you might say, well, I want a button. Okay, I'm going to put a button on the screen. So here I want to create a object for a button. Okay. This particular factory can also can reduce a drop down, can also reduce a slide. Okay. But I'm not concerned with that. I'm concerned with the button. But I can build in all those other types of abstract objects and it not be known to me because I'm not concerned with it. So that's what's being described here. Abstract factory pattern creates groups of related objects through a common interface without the client knowing exactly what classes are being created. I'm only concerned with the one that I need at this time. Okay, a builder pattern. A builder pattern uses complex object construction. Here I'm creating a user, and when I'm a user, I'm building a name, I'm building an email address, I'm building an address, I'm building who are my family members. All the details are here, and then I'm going to take it. I'm saying build. Build a commonly using build pattern means finish constructing the object and return it. So I'm putting in the details for the object. I'm creating the details. And then at the end of doing that, I say build it. Okay. Yep. This is not really different than what we're doing in creating new classes, other than, again, it's basically taking everything that I need in that class as far as the constructor, building that information all in one place. Okay. And then just say, hey, I finished implementing or storing all the information in various fields, build it. Okay. Benefits, immutable objects. Immutable just says that at this point, once I create an object, it's not going to change. And that's what we're doing here. We're setting values that, in this particular case, for this particular object, okay, these are the values, and the values are not going to change. Clear configuration, easy to read, lined up, okay, and avoids telescoping constructors. Here, we should look that up. What is telescoping constructors? Okay. Now look, and again, you'll see me do this quite often, and I'll say it again. So nothing else in this class, you'll realize that if there's something that you don't understand, what do I say do? I say go look it up. Okay, go look it up. If you're seeing a term telescopic constructors, telescoping the constructors, you know what a constructor is, you know what telescoping is. Look it up and see, does it apply to you? Do I need to know the benefits? Because if I'm not avoiding telescoping constructors, what does that mean? And that is going to be a situation that when I'm building objects, I'm going to say, hey, I have this problem with constructors, and I'm basing in a builder pattern. How do those two relate? So you can come back here and say, okay, this particular, if I have a builder pattern, then I'm going to avoid this situation with telescoping constructors. Okay. Again, basically understand what is involved in the pattern, and then based on a problem that you might have or a problem you want to avoid, you'll take that information and you'll basically pick the pattern that makes sense for your particular situation. Okay, key insights as far as patterns are concerned. Creational patterns, the four that we just went over. Creational patterns they manage life cycle, they manage dependency clarity, they manage testability, and they manage object complexity. But again, bottom line, excuse me, I'm going to skip through here, this is when I'm creating objects. What are the patterns available when I'm creating an object? Okay, so we're going to move from creational and into structured design patterns. Okay, in instruction design patterns, we have adapter design patterns. We're going to talk about composite, and we're going to talk about decorator, okay, and facade. Okay, so in looking at those, again, what we're doing here, let me back up here, sorry about that. Let me move fast, right? Structured design patterns. Structured patterns organize object relationships. And as far as what the structure should be for relationships. And this first one, we're talking about adapter design pattern. It converts one interface into another interface. Okay, it's used when we have integrating legacy systems. into a new system, or we're wrapping third-party libraries. Adapter wraps behavior. Okay, so basically it takes the information and adapts some old code into new code that you need for your new system. So here a program expects a printer, but we only have a legacy printer being defined. It's an existing class, and it's incompatible because I'm not using legacy printer anywhere. Okay. So, but I want to use what legacy printer does. So here we're expecting that we were going to use this interface for printing. The adapter basically takes the legacy, okay, the legacy class, and basically overlays or builds it into the printer, builds it into the new class that I want to. So it's taking some old information, and here it's really all I'm doing is printing text. If I had a large complex series of commands that I was doing internally, I don't want to have to rewrite those. Okay. I want to stay those intact. So what I'm actually doing for the legacy printer is I want to take its content. I want to use the content for legacy printer. But again, I want to use it under the auspices of a printer, printer.print. Okay. So it's taking old code or taking code and rewrapping it. Okay. So here, client code, printer, new adapter, print. Okay. Short explanation, the adapter pattern allows incompatible classes to work together by converting one interface into another that the client expects. Why are they incompatible? Okay, that's one of the basic questions. They're incompatible because the method expected by the client, print, does not match the method provided by the legacy class, print text. Again, we're taking the guts of the legacy and we're basically wrapping it into our new class that we want to be, what we wanted to call, without having to totally rewrite the code. Again, usually it's if I'm basically looking at taking methods and classes from a legacy system, and I need to rewrap them into a new system. Composite design pattern. The composite design pattern allows individual objects and group of objects to be treated the same way. Okay. So looking at a drawing program, okay, you take one shape, say you had a circle, and then you had a group of shapes. All this is saying is that the idea is ever how I process a single object here, as far as the logic that I'm using, okay, to draw, I want to use that same logic even if I'm not doing a circle. Okay, this says group of objects. I could have like we had before, a square, a triangle, but I don't want to have to redefine individual classes for those objects. I want to define one class, and those objects, in essence, use that same class for execution. Yeah, so if ever you had that where you're saying, yeah, these two objects are different, but I'm looking at it and they're doing the same thing. Okay. That might be the opportunity for you to talk about using a composite design pattern. Okay, here's just the explanation. Okay, you expect that you would read through that. Okay, why it's composite? The program can treat one shape or many shapes. Okay, the decorator design pattern, it adds behavior dynamically. So in this particular case, just a simple example, I have I'm creating a object called coffee. And here you can see that I have a new class I'm creating, but embedded within that, okay, is another class. Okay, so I'm basically changing the behavior of the milk decorator by including some dynamic behavior. This might be, here is milk decorator. It might be chocolate milk decorator. And in which case I'm still going to be using the basic, but I'm having other activities I'm doing for the For the chocolate milk decorator, again, how that behavior works is dynamic. I'm just plugging in what the new functionality is, but calling it the same class. So the behavior base is based on what am I including dynamically in the creation of the class. Adds functionality without subclass explosion. Okay. Decorators wrap behavior. Subclass explosion is a design pattern, is a design problem in object-oriented programming where too many subclasses are created to represent different combinations of behavior. I have a chocolate milk. I have a milk decorator. I have a skim milk decorator. I have a 2% milk decorator. Okay. All of those are subclasses. What this does is say, here's a method where we can do the same thing without creating, 10 different subclasses for each of the different types of coffees that we're going to be operating in, just for an example. Okay, so instead of using a more flexible techniques, composition, interfaces, design patterns, developers keep adding new subclasses every variation, which leads to, and this again is kind of explanation of, what is this subclass explosion? Uh, here again, just what I just stated, I have a red circle, red square, blue square. I don't want to create a class creation for each one of those. Okay? Using this method here, I can basically compact everything into a concise set of instructions without having to use subclasses. Okay, facade design pattern. The facade design pattern is used. Simplify complicated systems by providing one easy interface to it. This is probably a very good example. So think of that you're at a restaurant, and there's no facade. Okay, what you have to do is you have to talk to the chef, you have to talk to the cashier, you have to talk to the drink station, you have to talk to the dessert counter. Yeah. But what this does is basically takes all these particular activities that I need to do, combine them into one, and have me access just one of those objects. And within those objects, it will have a capability to do all of this at one time. So, yeah, so rather than me doing these individually, the waiter becomes the facade. The waiter handles multiple interactions behind the scenes. I don't see the waiter talking to the cashier. Okay, but there's logic in there for that. I don't see that the waiter's talking to the drink station. Yeah, but there's logic in there for that. So here, just a simple example. Without facade, you're creating a class, you're doing a start for CPU. Okay. Here we have a class for memory. Here we have a class for hard drive. Okay, all these are components. Okay, so look at the logic for doing that based on not having the facade. But then look at if we do use the confade. Here we have a class we just defined as computer facade. I'm accessing, adding the CPU. I'm handling the new memory. I'm handling the hard drive. Okay, all in one location, one central location of logic, rather than this where I'm spreading it out. And I have more lines, more opportunities for making errors. So I've consolidated all that into one facade. And all I had to do is say HG read, memory.load, CPU.start. Very compact and very useful. Okay, and that's the other details in there. Read through that again and try and make sure that you understand what that process is and when we might use a facade and when we might not. Okay, now we're going to jump into behavior design patterns. Behavior design patterns manage our algorithms, communications, state changes. Okay, so here we have a strategy design pattern. It encapsulates algorithms, allows algorithm swapping without conditionals. Yeah. Well, without saying if this, then this, if that, then this. Okay. Removes if then else capability. Again, if you see the bottom line guts of it is I'm creating a strategy based on a new class here, but it's still a strategy. So I can change strategies with this payment strategy class that I'm building, for object I'm building, uh, where each thing I'm building has a different functionality. I can do create card payment. I can create pay by cash. I can create pay by debit card, but I'm still calling it a strategy. So by using that one strategy, I can basically, knowing that I need different processing, but I want to call it, okay, basically this using the same design pattern of encapsulating different processes into one object build. Object design pattern. An object pattern shows one object to notify many other objects when something changes. Okay, so I can basically here, short version is I'm basically putting in here that what particular uh, objects do I want to, or what particular class do I want to track. So here I'm creating interface observers, and I'm telling the process that says, okay, when I have a phone user, I want to know when somebody's using the phone. Okay, in this particular example. Okay, so whatever objects you want to observe, then whatever class you want to observe, you can implement observers for that class. So anytime something happens with that class, you'll get a notification that that event has happened with that particular class. So here's just walk through this and just understand. Uh, Again, you have the capability that says, I understand what it's doing, but tell me line by line, what is it doing? That's when you have an excellent opportunity to take this code line by line, run it through chat and say, hey, give me a line by line explanation of what's going on here. Yeah. Okay, and here this is just to show you that I'm subscribing as an observer whenever I create a new phone user. I'm also doing it whenever I create a new email user. And so we have different patterns that we can keep track of so that whenever something happens, we'll get notified. Okay, you got the command design pattern. The command design pattern turns a request into an object. Okay. Stores commands, passes commands around, and undo commands. Real life example: when you press a button, the remote doesn't know how the TV works. It just sends a command: turn on the TV, turn off the TV, volume up. Each button represents a command object. Okay, so the functionality that I want to do, the command I want to do, I'm sending it over as an object. It becomes an object that basically has both variables and it has logic behind it as far as what actually needs to be done. Okay, here's one talking about, turning on the light, turning off the light. Okay, what's basically what we're sending these over. Sending these over as objects, where the command is now become an object. And remember, the key thing here, what makes something an object is it has variables, okay, and it has methods, okay, that go along with those variables. So again, I'm not sending a message to say turn on the light. I'm sending an object that says turn on the light, and here's how you turn it on. Okay, so just kind of want to put that back in perspective of why we might want to take a command and send it over as an object because of what is going to be needed in order for it to execute. Then we have a state design pattern that encapsulates state transitions. Okay, I want to change the state equal open to state equal closed. So we define state objects, and those particular objects are going to control the status or the state a particular class is in. Again, something that you want more information on, delve into it, look it up, find out what it does. Okay, part four, inheritance. Okay, we know what inheritance is. We know what composition is. Inheritance creates rigidity. When I extend something, I'm extending unless I do an override. Okay, that it's being defined what capabilities I can and cannot do. Okay, and that's the rigidity part of it. What I inherit is what I got, unless I override it. So that's rigidity. Composition is flexibility. Composition is saying that with the use of an interface, I have a little more flexibility as to what I need to do. Okay. Instead of inheriting something, I'll call a interface that does the same thing. But I can also easily substitute that interface with another interface to do some other functionality and not having to create a new class extension. New behavior is injected. Okay, composition, more flexible, easier to test, support solid principles. Inheritance is not bad, but overuse of inheritance makes brittle design. The solid principle here, just S stands for single responsibility. One reason to change when I'm writing classes. Object open close, open extension, close for modification. For Lyskov substitution, subtypes must honor contracts. We've discussed these before in previous classes, so we can go back and kind of review those. Interface segregation, no client forced to depend on unused methods. And that is a very good point. When you're basically using classes and there's a lot of methods in there that you just don't use, that is really just garbaging and garbling up, making and debugging things because of all the methods in there that you're really not concerned with. Okay, D is dependency inversion. We talked about that. Depend on abstractions, not concentrations. So solid, SOLID, are represented by these acronyms and processes. Just kind of a highlight. Factory supports open close. Strategy supports single responsibility. Object supports the dependency and inversion principle. And again, am I expecting you to memorize this piece by piece? You won't be able to. What you will be able to, as you become more and more aware and using object-oriented programming, when you basically get into issues where you're not doing single responsibility, where you're not doing dependency inversion, those things, these items that I'm giving you, I want it just to be a tickler and say, I remember we did something about solid, and it addressed open extension, close for modification. Okay. And that's what I want to do. I want to be able to extend the functionality of this particular object, but I don't want to change it. I don't have to modify the code that's already there. I want it to be a tickler. Yeah, that's what my purpose is. If you get a tickler to go back and say, yes, I need to get more understanding of how I can make my design solid. SOLID. Okay, just when you might look at it and say, well, when am I overusing patterns? When am I misusing it? Patterns are often overused. Symptoms, too many abstractions, one class per trivial variation, complex hierarchies without need, factories. I only have two classes, but I'm creating a factory. Okay, stuff like that. Does this pattern reduce complexity or does it increase it? That is your basic question. Okay. That is your basic question. If you're planning to use a pattern, is it going to make things better, less complex, okay, or more complex? If it makes it more complex, you want to go to the alternative. That's what's being said here. Sometimes the best solution is just creating a simple class. Don't create a factory. Yeah. Uh, Professional maturity means knowing when not to use a pattern, and that will come through experience. Okay, communicating architecture intent, patterns communicate are communication tools. This uses strategy. When you basically put in a pattern that you're using, and you say, oh, it's using strategy, that is a key to other engineers or other programs to say, hey, oh, you must be using a decoupling algorithm with swappable behavior. Okay. When I use the UML style diagrams, class relationships, composite arrows, same thing. When I'm using this, that is a key to others who are going to be using it as to what I'm doing. So your documentation should explain why was the pattern chosen, what problem does it solve by using this pattern, and what are the trade-offs that I'm accepting that may not be totally be good all the time, but because of what I'm trying to do, the trade-off is worth it. The architecture takeaway: patterns are not decorations. They are responses to recurring design problems. You're putting in a pattern to help you with a problem that you're having with processing. They must be justified, measured, communicated, applied responsibly. Uh, Good engineers use patterns thoughtfully. Great engineers use sparingly and clearly. As far as the closing to this particular chapter 5, before we jump into chapter 6, today you've learned implementing creational, structural, and behavioral patterns. You evaluated object creation trade-offs, preferred composition when appropriate, when to apply the solid principles and what does that mean, detect over engineering, communicate design intent. Design patterns or vocabulary. It's one of the things I want you to remember. Design patterns or vocabulary, but architecture is judgment. Yeah, I can use the strategy. Why did I use it? Judgment is what separates developers from engineers, and we will see you next week. Everyone, have a good one. Bye.